This video is just going to look at some of the big themes that go through the first year of chemistry, other than the calculations, obviously, and equations, particularly when it comes to writing explanations for why reactions happen and why there are particular energy changes associated with different things. So the first thing to realise is, of course, that a lot of chemistry, particularly at A level, involves physics. Really, chemistry is the interaction of matter with other matter, and the reason that it's interacting is because of attractions between charged particles. So we don't talk in chemistry about gravitational attraction. The molecules and the atoms are too small for that, but we're really talking about positives attracting negatives, whether that be a positive ion or a negative ion attracting each other, or whether it be the protons in the nucleus of an atom and their attraction to electrons. So you'll get a lot of questions about how easy or how difficult it is to remove electrons from atoms, and that's going to relate to how far away those electrons are, which you should have already come across when you look at group 1 metals, for example, but also the charge in between and the relative charges, so how much charge there is in this nucleus. And we can even talk about chemical bonding in the same way, like whether something becomes ionic or covalent is a result of the electrostatic attractions between particles. Electro meaning electrical, and static meaning that the charges aren't moving like an electrical current, so that's why we have the word electrostatic. And so if we think about bonding, for example, if both of these atoms have got a positive nucleus and one or more electrons in the outer shell, so this could just be a hydrogen atom, for example, but I'm just going to show one electron just to say what I'm talking about. If you have two hydrogen atoms that came together, for example, and they got near each other, then there would become a point at which the two nuclei of the hydrogen atoms would have an equal attraction to both of these electrons. And that's because both of these nuclei, if these were hydrogen atoms, would have like the same pull, the same electrostatic attraction. These electrons would both be the same distance away from both of the nuclei. And this is where a covalent bond will happen. So a covalent bond is when the two atoms come together to a point, they reach a point in space where the two electrons are equal distance from both nucleus and they're equally attracted to both nuclei. Now, in some covalent bonds, that attraction's not going to be equal, and some elements are going to have a stronger attraction to electrons than others, and that's going to result in some uneven sharing of electrons, which you will discover at A level when you look more at intermolecular forces. But we also know that ionic bonding can happen. So when ionic bonding happens is if we now imagine that the atom on the right, if the nucleus here has a lot more protons, or if the atom is smaller to the point that the outer electrons are closer to this nucleus. So there could be two things that could happen. Either there is a lot more charge in the nucleus, so now imagine that this atom on the left is on the left of the periodic table, so it doesn't have so many protons, and then by the time we come across to this atom is a non-metal on the right of the periodic table, and now it has lots and lots of protons, or more than this one because this is on the left. And then that means that the electrons in the non-metal are more strongly attracted to the outer shell. So if this was sodium on the left and fluorine on the right, fluorine would have a much greater attraction. I haven't drawn all the other electrons in for fluorine, we'll just imagine they're there, because all we're really looking at is what's happening to the pair of electrons that, if it were covalent, would get shared. Well, they only get shared if both of the atoms have a roughly equal attraction. If this is a non-metal atom, then the non-metal atom will be able to attract the electron completely into its outer shell because it will have a stronger electrostatic attraction, which means that now we will have formation of ions, which means that the non-metal will become a negative charge and the metal will become a positive. This becomes now a completely different type of bonding. The bonding was not the transfer, so it wasn't the movement of the electron. The bonding is now what happens between the cation that forms and the anion that forms, and all the cations that could possibly be formed from the metal are going to be attracted to all the anions, so you get a lattice structure. So that's very different from the situation where they were sharing. So all of that can be explained simply by differing amounts of electrostatic attraction. So key ideas to use in your explanations when you start writing more longer answers about chemistry is talk about energy changes. So generally, certainly for your first year, it will get a little bit more complicated in the second year. We can say that a process is more likely to happen if it gives energy out. So exothermic processes are more likely to happen than endothermic processes as a rule. And then generally we can also compare if something does require energy, for example removing an electron from an atom, then a process that doesn't require so much energy in is more likely to give out energy overall. So we can compare either one thing being exothermic and another being endo, or more likely two things are endothermic but one of them requires less energy input than another. So a weaker bond to break or an easier a lower electrostatic attraction to overcome will give me a lower energy change or lower energy needed. Energy changes are linked to forces of attraction because we know that force is linked to the energy required to overcome that force. So if you have strong bonds, for example, then you will need more energy. So that will be very much important when we talk about melting and boiling points. Similarly, in a chemical reaction, if you form strong bonds, you will have a very exothermic reaction. And those forces of attraction, which this leads on more to what you probably didn't talk about as much at GCSE, depends on the size of the charges. So again, we're thinking about how many protons are in the nucleus, or maybe the charge on a cation, like is it a 1+ or a 2+, and how far apart they are. So it's just like any other attraction, like magnetic or gravitational, it really depends on how far apart those two attractive substances are. So then we can think about the size, like the number of shells there are in atoms and ions will make a difference to the distance between the attractive charges. So we're going to look at some examples of how we could use this idea of energy, forces of attraction, and the charge and distance ideas. So we've got magnesium oxide and sodium chloride, and we're told that magnesium oxide has a higher melting point. So looking at the periodic table, these are both ionic compounds, metals and non-metals. Magnesium is a 2+, oxygen is a 2-, whereas sodium is a 1+ and chloride is a 1-, and they're all in the same row of the periodic table with the exception of oxygen actually, which is in the top row. But really the main difference here is the size of the charges. So they both have ionic bonding, we're not comparing different types of bonding. So it's simply that Mg2+ and O2- have bigger charges, and actually because they have bigger charges they'll also be smaller ions. So if you imagine the Mg2+, although it has the same number of shells, so technically they both have 2 and then 8, if we were to draw out their electron arrangements of the ions for Mg2+, Na+, but of course magnesium has got that one extra proton in the nucleus, so actually it would be a little bit smaller because those 10 electrons would be more attracted to the nucleus. But for now, let's just say that magnesium 2+ and O2- have bigger charges, and what I should do there is not finish my sentence, because when we make a comparison we should also say what we're comparing with, Cl minus. So therefore, that's a little shorthand you can use, the electrostatic attractions between ions in the lattice are stronger, and then we need to make the energy link because melting point is what the question was about, and so therefore need more energy to break bonds, overcome the attractions, however you want to say it. So that's one example for where you're looking at two ionic compounds. They both have ionic lattices, but they have very different melting points. Magnesium oxide, if you're curious, is about twice the melting point. It's about 800 and about 1600 degrees for magnesium oxide. Okay, this is more familiar. You've done this one at GCSE, probably. Why potassium is more reactive than lithium. Let's just A-level the answer up a little bit and make it a little bit more specific. So we're thinking about attractions, charges, and energy when we're answering this question. And when we're thinking about attraction, we're thinking about distance and the charge. So potassium is further down the group. So we can say that potassium has more shells, or you can say a greater atomic radius. And when they are reacting, we're trying to lose the electron in the outer shell. So a greater atomic radius. So that means that the outer, I'm going to underline that, electron, because obviously there are a lot of electrons in potassium and lithium, and the inner electrons are actually going to be closer to the nucleus because there's a bigger nucleus with more protons in it. So the outer electron in potassium, be specific all the time, is further from the nucleus, and therefore less attracted to it. You could also talk about shielding here. So there are more shells between the nucleus and the outer shell for potassium. So the inner shells. So that's sort of charge and distance. So the distance thing is because there are more shells, obviously it's further from the nucleus. And then the shielding thing is suggesting that the charge on the nucleus is kind of less because of the electrons that are in the way, even though genuinely, obviously, potassium has a much bigger nuclear charge. So it's further from the nucleus and less attracted. And therefore, maybe at GCSE we might have said that outer electron is easier to remove. Now we're going to say that the outer electron requires less energy to remove. It is energy in. So a lot of people think that because group 1 metals very readily form, very readily lose their electrons, that somehow that's lower in energy after it's lost its electrons. You do have to put in energy always to remove an electron from an atom, because remember that electron is attracted to the nucleus. Even if it's more weakly attracted, it is still overcoming attraction. You're not bringing two attracted things together. Okay, so we've talked about energy, we've talked about charge, we've talked about distance and attraction, so we've covered it all. Example number 3, explain what a covalent bond is and why breaking a covalent bond is always endothermic. Well, lots of people, even when they're quite a long way through their A-levels, often say that a covalent bond is the sharing of electrons. But that hasn't explained the bonding part. That hasn't explained the electrostatic attractions, because that's what all bonds are. So what a covalent bond is electrostatic attraction between the shared electrons, so we do want to put that in there, I'm going to say a shared pair of electrons because each covalent bond is one pair, and the nuclei of the atoms either side. So that's what a covalent bond actually is. It's always endothermic because this is an attraction between charged particles, and you need energy to overcome the attraction, and that's why covalent bonds always require energy to break them. And actually, the smaller and the shorter a covalent bond is, the closer those nuclei are with the less shielding to the shared electrons, then the stronger that bond generally is.